Okay, let's dive into this. Today, we're unpacking Chapter 6 of Chip Hoyin's incredible book, AI Engineering. Now, this chapter is an absolute goldmine. It covers both retrieval augmented generation, or RAG, and AI agents, including how agents use tools, plan with chain of thought, and manage memory. But to really do the material justice in this explainer, we're going to laser focus our journey today entirely on RAG. This is the exact architecture that lets modern AI systems read a company's internal documents and answer questions accurately without just hallucinating facts. Let's explore exactly how it works. So here's our roadmap for the journey. We'll start by looking at the core RAG architecture, then we'll move through term-based retrieval, explore semantic and hybrid search, dive into retrieval optimization, and finally push the boundaries with multimodal and tabular RAG. All right, first stop on our journey, setting our mental model for the RAG architecture. Now, what's really interesting about this setup is that it solves a massive problem. Large language models are incredibly smart, right? But they have severely limited context windows. If your enterprise knowledge base spans 500 pages or sits in a massive database, you literally can't just shove all of that into a single prompt. It's way too big, it's incredibly slow, and honestly, it's just too expensive. The elegance of RAG is that it introduces this brilliant two-step process to solve the bottleneck. When a user sends a prompt, a retriever first takes that prompt and searches through your external memory, so things like documents, tables, or chat history. It fetches only the absolute most relevant chunks of data. Then, and only then, it passes both the original prompt and that newly retrieved context to the generative model, which actually crafts your final response. So it turns out RAG acts as this highly selective filter. And why does this matter to an AI engineer? Well, because every single extra token of context you feed into an LLM costs you money, and it adds latency to the response. Plus, if you just hand a model a massive document, it often kind of loses focus and pulls from the wrong sections anyway. RAG ensures the model only sees the needle, not the entire haystack. It's a real game changer for performance. Moving right along to Section 2, term-based retrieval, which is really the lexical foundation of all search. To understand this, think of an inverted index, kind of like the index at the very back of a massive textbook. Instead of scanning every single page of every document when a query comes in, the system just checks this dictionary. If you search for the word machine, the index instantly tells you it appears in 4 specific documents, and it even tells you exactly how many times it pops up in each one. It's an incredibly fast, super efficient lookup mechanism. Now, you might be wondering, with all this new AI tech, why on earth do we still use these older algorithms? Because algorithms like OCampi BM25 are just formidable baselines. They are absolutely still industry standards. They work by looking at term frequency and inverse document frequency, but crucially, they normalize the score based on document length. A longer document is naturally going to have more instances of a word just by pure chance. These systems account for that. They're lightweight, incredibly fast, and very cheap to implement compared to running modern neural networks. But they do have a major failure mode. To use a term-based system, you have to split a user's query into individual words, a process we call tokenization. So what happens if someone searches for a hot dog? If the system splits it up into hot and dog, the original meaning is completely destroyed. You're going to end up retrieving documents about sweltering summer weather and golden retrievers, right? Engineers can mitigate this a bit by indexing common multi-word phrases. We call those n-grams. But ultimately, term-based retrieval is pretty much totally blind to actual human meaning. Which brings us to Section 3, semantic and hybrid search, retrieving by meaning. The core difference here is pretty profound. Lexical retrieval is superficial. It's just asking, do these exact letters appear in the document? Semantic retrieval, on the other hand, asks, does this document mean the same thing as the user's query? And it achieves this magic by using vector embeddings, essentially mapping abstract concepts into a mathematical space. And this brilliantly illustrates why semantic search is such a game changer. Just think about the word transformer. If you use a basic term-based search, you're going to pull up documents about power grids, Michael Bay action movies, and AI neural network architectures all mixed together in one messy pile. A semantic retriever actually understands the context of your query. It matches the mathematical meaning of your request to the correct documents, leaving all that irrelevant stuff behind. So here's how that works in practice. Both your external memory documents and the user's query are passed through an embedding model. That's step 1. This model translates human text into a dense vector of numbers. Then, in step 2, the system compares the query's numbers against the database's numbers. the data chunks with the closest mathematical distance are fetched and sent right to the generative model. The whole retrieval process literally happens in this shared mathematical space. Interestingly enough, though, AI engineers rarely rely on just one single method. They actually combine them into what's known as hybrid search. You might use a really cheap term-based search to grab all the documents containing a specific keyword, and then use vector search to find the ones with the right semantic meaning. To merge these results fairly, engineers use an algorithm called reciprocal rank fusion, or RRF. It assigns a score based purely on rank. First place gets a score of 1 over 1. Second place gets 1 over 2, so 0.5. It then sums up these scores across all the different retrievers to give you one master, perfectly ranked list of documents. All right, let's move into section 4, retrieval optimization. This is where we fine-tune the journey. This is honestly where AI engineers really earn their keep. First up, we have the chunking trade-off. Before you can embed a giant document, you have to split it up into smaller chunks. But here's the catch. There is no universal best size. If you take your chunk size and cut it in half, well, you suddenly have twice as many chunks to index. That means twice as many embedding vectors you have to generate, store, and search through. Your computational overhead skyrockets and your query speed plummets. It's a really delicate balancing act that requires a lot of real-world experimentation. Once you've retrieved those chunks, you often need to apply a secondary filter, which we call context re-ranking. Say you pull 50 documents, but your model can only comfortably process 10. A re-ranker acts as this highly precise filter to pick the absolute best ones. This is especially vital for time-sensitive applications. If you're building a stock market analyzer or a daily news aggregator, the re-ranker can artificially boost the score of recent data so it doesn't get buried. Also, keep in mind, LLMs actually process information differently depending on where it physically sits in the prompt, so ordering these chunks correctly is absolutely critical for good results. Okay, I want you to imagine a user typing this exact phrase into a database. How about Emily Doe? Just take a second and think about that. If an isolated retrieval system gets this prompt, it is going to fail miserably. It has absolutely no idea what you want to know about Emily. And this completely highlights the necessity of query rewriting. In a real conversation, the previous message was probably something like, "When was the last time John Doe bought something?" By using a secondary, smaller AI model to rewrite the user's prompt based on that conversational context, How About Emily Doe magically becomes a highly specific standalone query, "When was the last time Emily Doe bought something from us?" And crucially, if the system can't figure out who Emily Doe is from the history, the rewriting model is trained to acknowledge that the query is unsolvable, rather than just hallucinating fake context. Now, sometimes highly specific strings get mathematically smoothed over and lost when converting text to vector embeddings. The really clever workaround engineers use for this is contextual retrieval. They inject hard keywords, tags, or metadata directly into the document chunk itself. So by appending something like a specific obscure server error code, say EADDR not avail 99, you ensure that if a user searches for that exact string, the system can still find it effortlessly without it getting lost in the math. Finally, Section 5, multimodal and tabular RAG. We are really expanding the horizon here. Imagine a user asking, "What's the color of the house in the movie Up?" We're no longer limited to just searching text anymore. The retriever doesn't just pull text descriptions, it can actually pull an image of the house with all the balloons tied to it and pass both the text and the image straight into the generative model. This works in one of two ways. Either the image has text metadata attached to it, like a descriptive caption that the system searches through, or the system literally searches based on the raw visual content of the image itself. To search by visual content, engineers use a multimodal embedding model, something like CLIP. And the workflow here is absolutely fascinating. In step 1, CLIP generates mathematical embeddings for all your text and all your images, storing them together in the exact same vector database. In step 2, the user's text query is converted into that exact same mathematical format. In step 3, the database just looks for the closest numbers. It's wild to think that the model understands that the word balloon and a literal picture of a balloon map to the exact same mathematical neighborhood, making this cross-format retrieval completely seamless. But as we look to the future, there is one massive challenge remaining: tabular data. Most enterprise knowledge isn't just unstructured text and images. It's vast SQL databases and complex Excel spreadsheets. The book notes that augmenting a model with tabular data behaves by entirely different rules than the standard RAG we've discussed today. So I'll leave you with this provocative thought. If standard RAG can't easily read a spreadsheet, how will you redesign your pipeline to unlock all that structured knowledge? And beyond that, How do we eventually give these models the tools to act on that data as autonomous agents, navigating environments, using tool inventories, and planning with chain of thought? Well, that's a whole other fascinating half of this chapter we'll have to explore another time. Definitely something to think about as you continue exploring AI engineering. Thanks for diving in with me today.